There are a lot of challenges in adapting different I/O structures to training material. Not everyone that uses the training material has the identical processor and I/O modules that we used. Fortunately, with the Logix engine using RS Logix 5000, you have a lot of latitude in how you configure your I/O. Virtual I/O, mapping I/O, and buffering I/O. Three completely different things. Virtual I/O is just creating a user-defined data type that looks like a module-defined data type. Mapping I/O is actually taking, for the most part, scattered inputs and outputs and mapping them into common module-defined looking tag structure. So let's say that you had 3 inputs available from one card and 2 from another, and then 1 from yet a third input card. You could map those 3 into one integer or double integer and make it look like they are contiguous I/O points. And then of course buffering I/O is very important for the Logix engine, simply because with Control Logix and Compact Logix and matter of fact all of the RS Logix 5000 family, the I/O is not updated synchronously with the program scan. Whereas with, we'll call it the 500 arena, which would be Slick 500s and MicroLogix, they could not chew gum and walk at the same time. So they would collect up snapshots from all of the input modules, put that in memory locations, then your logic would execute using those memory locations, those snapshots, and update other memory locations. And when the program scan is finished, it would take and transfer those output images out to the actual output cards. With 5000, that's not the case. With 5000, you have a requested packet interval, and you can, plus you have change of state, which is another feature. The long and short of it is, during the time that you're scanning the program, the I/O can actually change. In other words, the inputs are updated on their own. The input cards actually update the processor's memory. It's not like 500 arena where the controller had to stop what it was doing and go out and operate all of the modules in the backplane like puppets. In other words, activate each module one at a time, collect the data into input words, then execute the program, and then stop executing the program, go and take all of the output images and transfer them out to cards on the backplane. And that's why they call it an active backplane, is because the processor has to activate through the control bus each module one at a time, either collect information or transfer information out. With 5000, that's not the case, because the I/O modules are smart, at least they are for Control Logix, the 1756 I/O modules. And besides that, Compact Logix, which uses the 1769 I/O, along with Point I/O, although those I/O modules are not smart, the chipset in the Compact Logix processors, it has a separate chipset that can collect the I/O basically on an RPI, which means that the input image gets updated completely independent of the scan of the program. For that reason, writing a program where in your first rung or your first couple rungs, you look at the state of an input and then make a decision, and by the time you get to the end of the program, you're assuming that decision is still good, where in fact the conditions in that rung earlier in the program have now changed, and had you executed that logic again, you would get a different result. To avoid that, they do something called buffering I/O, and that is where the very first rung in your program, you take and copy the snapshot of an input module into another tag, and then you use that tag and the bits of that tag to write your program with. So you're not directly using module-defined tags. You're transferring the module-defined data into just an integer or double integer. So that integer or double integer only gets updated once at the beginning of the program. And then in the course of your logic, we'll call them outputs if you like, they go to a standard integer or double integer. And when you get to the end of the program, then there's logic that transfers, we'll call those output bits that you put into integers or double integers. It transfers those into the module-defined output data tags. That's buffering I/O. A quick review of data types. Over here in your controller organizer, you have a category, data types. Everything in memory will fall underneath one of these categories and a class of objects underneath this category. I eliminated everything from this program, and including the tags. Now in 500, we'll call it 500 meaning including PLC 5, Slick 500s, and MicroLogics. There was a database, and that database could include internal bits, which we could do here too. So when I go to look to see if everything's cleared, I go to two places. I go to the controller tags, and I see it's empty, and notice it says show all tags. You can actually configure what tags you want to show and don't want to show. But when you see this symbol right here, it says display tags in selected scope. This is controller scope. That symbol right there is the processor. I'll close that and then click on program tags. That's the only other place to look. And again, it says all tags. And the scope shows main program. And the main program is what we just opened the tags under, program tags. So we know that right now there are absolutely no tags assigned. I even deleted the two I/O modules that were connected to this backplane, and when I did that, I also deleted any module defined tags. So we have 5 categories here. The only ones we're interested in right now are user defined, predefined, and module defined. We don't care about strings, and there are no add-on defined data types until we have add-on instructions, which we definitely are not covering in this manual. Let's look at the first one. And remember, user defined, we don't have any, so there's nothing to look at. If there was a plus sign here, then there would be some in that category. So we have predefined, and that's it. We don't even have any module defined. So if I open up predefined, I get a whole long list of predefined data types. Now some of these are atomic data types, like single integer. If I double click on that, nothing happens because it's an atomic data type, meaning there is no definition beyond the fact that it is a single integer, meaning an 8-bit word. And if we slide on up here, the next one we see that's an atomic data type is real. If I double click on that, nothing. A real data type would be floating point. That's normally what we call floating point. And if I keep scrolling up until we get to long integer, if I double click there, see again, we don't see anything. A long integer is bigger than a double integer. It's 64 bits. I've never used any. An integer is 16 bits. And then, of course, we have one left. Well, we have the double integer, which is 32 bits. And we have a Boolean, which is 1 bit. Those are your atomic data types. If you double click on them here, nothing will pop up because it is an atomic data type. It is an atom, so to speak, compared to a molecule of data. Now, to pick something that's a molecule of data, made up of atomic data types, let's pick the counter and double click on that. See, now we get something that pops up, and we see that we have 2 double integers and 5 Booleans. 5 bools, if you like, or Booleans. Booleans. We have a preset, an accumulate, those are 32-bit values, which means that you can count up and down to quite large numbers. My point is, though, a non-atomic data type is made up of atomic data types. In this case, this is made up of dense and Booleans, two data types. If we pick this one right above it, you'll see that this is made up of, I see dense, Boolean, and I see real right down here, 8 real. Actual position, it's in floating point. Okay, so we'll close these. Those are predefined data types. And that's really all we have right now. We don't care about strings, and there are no add-on and user-defined. So the first thing I'm going to do is cause some module-defined data types to show up. Module-defined, they're called that because when you add a module into your structure, your controller environment, whether local or remote, you're adding an I/O module. That I/O module is an information object. And that information object could be made up of one integer, more than one integer, double integers, Boolean, real, and other data types. So I'm going to add one new module. And notice that there's no module defined data types right now. So I went to the backplane, and now I'm going to type in IQ, because that's the module that we want to add. That's the module for our combo 6 inputs and 4 outputs that we use in our lab project. I'll click on that, say create, thinking, thinking, thinking. You saw this flicker in the background because it's adding it into the project. Now it wants a name for that module. You can name it anything you want, but since we're putting it in slot 1, I'm just going to call it DC1 underscore 6 in 4 out. Now I could call it monkey doodles. The name doesn't matter. I typically try to give them a name that makes some sense to me later on when I'm looking at them. Now I don't know what the series is or the revision level. However, there's an easy way to do that. I'm going to go out to RS Links and open it up, and hopefully remember to move it into your field of view. I can see that I did not do that with this. After I picked this and I came down here, clicked on create. So I'm going to go ahead and close that, and I'll open up the properties again for this so we can continue where we were at. Okay, I had revision. Whoops, I clicked on the wrong thing. Oh, you know what? When I deleted it, I deleted the I/O module, so we have to do that again. But let's go out first and look to see what we have. There's the Ethernet card. There's a local bus. And there's our combo module. So I can see right there it says B firmware revision 3.1. I can also right click on it, device properties, and you can see that it's revision 3.001. So I'll close, minimize that, go back here, new module. This time I'll pull it up in view, IQ, double click. Now see, this is revision 2. I'll go ahead and change it. That really isn't part of this lab, but there it is. Now it's right. And I'll leave this compatible module. I could make it exact match since I went to all the trouble of making it an exact. We'll leave it compatible. And OK. Now what I want you to see is, now that we've done that, look, we have a plus indication in front of module defined. Remember, there was nothing there before. So when I open this, I see 3 module defined data types. One for C for configuration, I for input, and O for output. If I double click on this, I can see what that module defined data type looks like. That's the name of it. That's the generic name for any 1769 IQ6X OW4, period. If I add 10 of them, I won't have 30 here. I'll still have these three because these are the class of objects. And I'll close this just a second. I'll go up here to controller tags. These are instances of that class of objects. To emphasize that, you see right here, data type. See over here, data type. This local :1:C is an instance of this data type right here. And you can see it's verified over here. Same thing for these others. So if I were to go back and add another IQ6 so forth, IQ6, double click, for fun, slot 2, we won't change anything about it. And we'll close this. Now you see we have 2 down here. And we have 2 instances here. See right there, local 1C is that data type. Local 2C is the exact same data type, and we still only have 3 module-defined data types brought into our project. If I had 100 of these modules, I would still only show these 3 right here for module-defined data types. If you want to call these the templates, but in proper data terminology, they're called a class of objects, of data objects. Each one of these has a data structure made up of atomic data types. We already looked at that one. You can see you've got an integer, a Boolean, and 4 single integers. Those would be 8-bit words. This one, we have a double integer and 2 single integers. And the last one, the outputs, we strictly have data. A single integer, 8 bits. Now we only have 4 outputs. So 4 of those 8 bits represent the outputs that are going out to that module from the controller when the I/O update is in effect. So I'm going to cancel this. User defined. Okay, I'm going to delete this module simply because I only have one in there and I don't want to convolute what we're doing here. So I'm going to go to user defined. I'm going to create this. You did this in your lab, new data type, and I called it data. And I gave it the name data. Don't let that confuse you. This name could be anything, but we want this to be data. Or this could be anything as long as this is data. And the data type that we want to use for the user-defined data type called data is we want to use integer. And now you could just type in a I, N, and then hit enter. Okay, and that's all we have there for the data type, user-defined. See, data. Double click. There it is. Now you can edit this. And by the way, if you use this in 47 places in your project and you go and edit this, it changes all 47 of them. It has what's called inheritance. Good stuff. Okay, next up, I had you create another data type, user-defined data type, and we called that local inputs. And for a name, we simply put I. And for data type, we put the one we just created before. If we type in D8, there it is. Hit enter, and you're done. And we also did the process for local outputs. So we created one more user-defined data type, which we call local. And we put in an O, uppercase O, and we said the data type was data. I know it sounds like double talk, but it's not. Okay, so now we have a user-defined data type that we're calling data. And then we have local inputs that we named I of the data type. So I will have 16 bits of data. O will have 16 bits of data. All real I/O will always be found in the controller tags. Okay? And here's the one module that we have in slot 1, right here. See down here? Slot 1, 1769 IQ6 XOW4. That's it right there. And it's made up of these data types. This is real I/O. It will always be found in the controller tags. Real I/O or module defined data types cannot reside in the program tags. We went over all this before. It doesn't hurt to review it. However, what we're going to do now, we can do it in the program tags or in the controller tags. Now I had to do it in the program tags in the lab, so we'll do it there. So I went in and I created a tag local_3. So we went in there and we made it local inputs. Okay, now if we expand this, we have local3.i.data.0 through 15. So see, this looks very close. As a matter of fact, I think I'll just move this. I'll cut this, then go to controller tags, edit tags, and I'll paste it in here. So you can see that how close it looks to these. Okay, you see local:1:i.data.0. Local, but instead of a colon, because we can't do that in a tag name, we have an underscore, and then we have the slot number, then we have i.i.data.0. So other than the underscore here and the colon here, they look identical. However, this is nothing more than really than an integer, a 16-bit integer. That's all there is in there, is this data type, which has got 16 bits. So this is not an actual I/O module. You could call this virtual I/O because it looks like I/O, but it's not. But remember that now this is 8 bits and I made that one 16. I made it 16 because a lot of you may be using IQ16s or using 16-point input modules. I could have made it a single integer. I could go back and redefine. Let's see if I can get away with that. Redefine it as a single integer. See if I got away with it. Yes, I did. Now, if you were online, it wouldn't let you do that. You couldn't do that online, but you can do that offline. In the lab, I probably had to use an integer simply because a lot of you may be using 16-point input modules and not something that uses 8 bits. So as a matter of fact, I'll change that back. I'm going to just go to here, change that to INT, enter, apply, I get the message, yes, okay. Then I come back here. Okay, so this is virtual I/O. I/O mapping is a little bit different. So I will go to the main routine. As a matter of fact, I think I will create another routine called I/O map. Now in the main routine, of course, you would have to have a JSR that went to I/O map. Otherwise it won't execute. So we go to I/O map, and then we put in, I'm just going to grab something out of the breeze here, and I'll make it local. Now, this is real I/O. So I'm going to grab bit 3, and I'm going to move it. Now go define it as an integer. Okay. Now notice that the E's are still there because it does not like something here, and I can tell you exactly what it is. That's a 16-bit word they're in, and this is a Boolean type instruction. So we'll just double click on there, and we drop this down, and okay, now that's input 0. So we used an actual input, the 4th input, bit 3 of some I/O module, and we'll do another one, XIC OTE, and we'll just make that one 13 and make that in bit 1. Now it doesn't like something here. Oh, I forgot it that I bumped it down to 8 and I put in 13. So we'll make it 6. And you see now it's happy. So your input 0 and input 1. But in reality, on the I/O module, it's input 3 and input 6. So this is called mapping I/O. You are mapping scattered inputs into something that's sequential. Yeah, something sequential. So it looks like consecutive or contiguous bits in a word. And it is. This is bit 0 and this is bit 1 of the integer data type tagged as IN. So that's mapping I/O. Now, if you use these in place of these in your program, then these are buffered because these two rungs, in other words, if I have some logic now, and I have input 1, not input 0, start timer 1, define that as a timer data type, preset as this program executes, it's going to look at this bit in memory, which came in from an actual input module. Then it's going to set this bit to match. Same thing here. And then let's say that this rung right here represents, just the beginning of your logic, which goes on for a couple hundred rungs. Well, these two bits will follow whatever this is at the beginning of the program. In other words, at the beginning of the program, this rung is executed, and whatever bit 3 is here of that input module will set this bit to 1 or 0, and the same thing with bit 6. But the states of these two bits will not be visited again until it's all the way through the program and comes back and starts again. So you can rest assured, as you use these memory locations in your program, they won't change on the fly while you're executing the program. Now typically, instead of mapping in scattered bits, they'll do something like this. They will have an unconditional move, which is really a word copy, and they will take and move the whole single integer into I'm going to have to define inputs. As a matter of fact, this was slot 1, so I'll make this 1. Inputs 1, and we'll make this a single integer. Now, in this case, you're moving all 8 of the inputs into these bits at the beginning. This is called mapped because 3 and 6 aren't contiguous, but 0 and 1 are. So effectively, these are buffered. These 2 inputs are buffered into these 2 bits. This is an example of buffering the whole card, all 8 bits. Or if that were an IQ 16, we can do one of those. We'll go down here, new module, IQ 16. DCN 16 slot 2. Okay, see, now we've added one more module defined data type, which has fault and data. Real simple card, nothing to it. So if I were to do the same thing, buffer that module, and we'll keep them in order, it really doesn't matter. And I'll just drag this over here because I'm lazy. I'll go change this to a 2. And drag this over here. Change that to a 2. And of course then I have to go define it, but it can't be a single integer because this is a 16-point card. So it's just an integer. So you see here we have 8 bits and here we have 16. We've now buffered that input module's data into this word and that input module's data into this word. And so you can now use these tags so we'll do a inputs INP INP of course we need it to the bit level. And for outputs, we'll put 0, 1, because remember we do have some outputs for 0, 1. We didn't define that as a tag, and we're going to define that as a single integer. And then go give it a bit value. And then at the end of the program, we're going to take and unconditionally move output 1, outputs 1, but the whole word, we're going to move it into local there. So the actual word in memory that stores the state of the bits that are going to go out to the output module doesn't get updated until all the way at the end. Typically, these output module defined data types would have gotten updated all the way through the program. So we basically have buffered our I/O. Here we buffered local 1I data into inputs slot 1, and we also did local 2I data into inputs slot 2, and then for the outputs we did the same thing. That's buffering your I/O.